Sup, bees? Okay, so let's do 2.4, work and energy. So basically, question is, let's say you have a charge and another charge, and you want to bring this charge and put it here. How much work are you going to have to do? That's the question. Well, it turns out the work is force times distance. You know that, F dotted into dl, integral from a to b. So it's the change in potential at point B minus point A times the charge that you're bringing in. Okay, so there's your equation there. The potential difference is equal to the work per charge to go from some point A to point B. For example, if you want to bring a charge in from very far away and stick it at point R, right, the potential at infinity should be 0, and you bring it in and you get that work is equal to just a charge times the potential at that point. That's the energy required to put the charge there. So that makes sense. For a collection of point charges, the work required is the potential. Okay, and we know the potential set up by a charge is 1 over 4 pi epsilon naught q over r, and then q times that potential is this, and you bring in another charge, okay, then you add that to it, and then you bring in another charge, you add that to it, and you bring in another charge, and you end up 4 charges, bringing them all in, you end up with this R1, and you got to add all the little components up to get your total work. So it's as simple as that, and so if you kind of work through this, the total amount of work is 1/2 times the sum of the charges times the potential at those points, okay, which is kind of cool. So you got some problems here. You got 3 charges at the corners, like this. How much work is required to bring in another charge from far away to put it there, okay? And all you have to do is calculate the potential at this point, from the potential at this point plus the potential from this one, plus the potential at that one, okay, and then charge times the sums of those potentials. Okay, so you got to figure out what the potentials are, and then do Q times that, and so on. And then how much work does it take to assemble the whole configuration of 4 charges? Okay, then you start with 1, you bring in the second one, you bring in the third one, you bring in the fourth one, so that's the total amount of work. All right, so your main thing there is calculating R, the separation of the two. All right, so how about for a charge distribution? You just have an integral instead of a summation, 1/2 times the integral of the charge density times the volume, times the potential times d tau. Okay, so you've got some smear of charge, you want to bring it into some other smear of charge. Question is, how much work does it take to move this smear of charge to here? Well, it's the integral of the charge, the smear of charge times the potential there. And then they've got the line charges and surface charges, depending on the whatever thing. But we also know that del dot E is equal to rho over epsilon naught. And so if we use that and say that rho is equal to epsilon naught times del dot E, and then plug that into there, then we become world champion of electrodynamics, okay? And you get this thing, okay? You may be thinking, well, I don't feel like a world champion yet because this looks crazy. Basically use integration by parts to get rid of the derivative on E and transfer it onto the potential here. And then you get this nice thing, which is easier to calculate, because we also know that we can write the divergence of the potential as the electric field. So then we end up getting E squared times the surface integral. But there's something really cool here, because it doesn't matter what the volume is that we're integrating over. We can use any volume as long as it contains the charge. And it turns out that if you make your sphere arbitrarily large, the electric field very far away is 0, if your reference point's infinity. So this integral should be 0 really far away, because you're going to have no electric field going through your surface area if this integral is taken to be, over all space really far away. And so if you take the integral over all space, the surface integral goes away, and then you're just left with integrating the electric field itself through all space, and then you get that the energy is epsilon naught over 2 times the integral of E squared d tau, which is pretty cool. So if you calculate, if you know what your E squared, if your E field is, E squared, E dot E, for example, integrate that over all space, and then you get the energy, which is pretty cool. So, for example here, let's say you've got your work, you've got your definition here, and you want to know what is the energy of a uniformly charged spherical shell, okay, which means it has a surface charge, density, blah, blah, blah. So we're going to take our surface charge, integrated over with the potential over the area, and then we remember that the potential at the surface of a sphere from a previous problem is 1 over 4 pi epsilon naught times q over r, okay, and so then we integrate that, and then we just have sigma dA here, which is the surface charge times the area, which is just the charge q, and so you get 1 over 8 pi epsilon naught q squared over r. But then we could do it a different way using our new fancy equation here, and we can say that inside the sphere we have E equals 0, and outside the sphere we know that E is kq over r squared, or 1 over 4 pi epsilon naught q over r squared. So then E dot E is just q squared over, whatever, and then r dot r hat dot r hat is 1. So we get this. So then we integrate this over all space, and we get a 4 pi from the integral over all the angles, and then we just have the 1 over r squared to integrate, and that gives us 1 over r, and then again infinity gives us 0, so we get the same answer doing these integrals both ways, which is pretty cool. Okay, and find the energy stored in a charged sphere 3 different ways. Okay, so you'll do that too. Now there's this little bit of a confusing section here that's saying that equation 2.45 implies the energy is positive. So if you look at the equation 2.45, then E squared is always positive, epsilon naught is always positive, E over 2 is always positive. So this energy, when you do this, you'll always get a positive number. But for equation 2.42, if we go back to that equation 2.42, if you're summing up the charges, well, you could have a plus charge, you could have a minus charge, you could have all kinds of things. So you could end up with a negative energy instead of positive. What's up with that? Well, it turns out that both are correct. It just depends what you're kind of talking about. So one of the things is that equation 2.42, the very first one, doesn't take into account the work necessary to make point charges in the first place, which is weird. You start with the charges already there, and bringing them in, depending on what you're trying to do, you get some weird stuff. So, for example, the point charge, according to equation 2.45, if you just have one charge, the energy of that one charge is infinity, which is stupid. That's at the point r equals 0, right? That's where we have this issue with a point charge. What do you do at exactly where the point is? And then he says the infinite energy of a point charge is a recurring source of embarrassment for electromagnetic theory, afflicting the quantum version as well as the classical. And then in chapter 11 he talks about this a little bit more. But anyway, so we just sort of have to ignore this for a little while, because it doesn't necessarily matter, but that's where this flaw comes from, is by ignoring that or embracing that. Okay, so then the question is, where is the energy stored? When we talk about the energy of a charged particle or whatever, when we talk about this energy, where is it stored? What is it? Well, he's saying in this case, you can consider it either in the field or in the charge itself. Okay, so he's saying either the energy is in the field or the energy is in the charge. the same energy density, these should be equal to each other. We know generally that the energy is stored in the field itself, but as far as we are concerned, you could consider the energy stored in either, okay, whatever. Now, the superposition principle does not work with the regular way. So, for example, since we know that the total energy is dependent on E squared, then if you want to add separate electric fields from separate things, you add them vectorially first, and then you square it. So you have to do E1 plus E2, then square it. If you do that, you get the magnitude of E1 squared plus the magnitude of E2 squared, but then you have the cross term here, E1 dot E2, that you have to take into account. So the total energy from separate electric fields, maybe two charged spheres, is the energy from one plus the energy from two, and then plus this extra interference term here, E1 dot E2, that you have to do. Okay, which is pretty cool. So what he's saying is if you double the charge everywhere, you quadruple the energy, which is a little bit cool. All right, smile you later.